recap. We have x, want to find x by solving, minimize this, okay? And then we are given a and b, and I just want to solve this. And here are some constant. Q is A transpose A, P is A transpose B, L is the two norm largest eigenvalue of Q, or the largest singular value of A. This is quadratic program, okay? And gradient descent, this is step size T, either use 1 over L or exact. So I will always do this. This is good practice. You type the code name gradient descent on QP. Day, so 2025 January 20. Otherwise you forgot what is that. Okay. And usually I save it as main. Okay, I call it main. Also I usually use this when variable here, file here, code here, the command here, and this. And then what? Okay, we want to do what? Minimize something like this, right? Half qxx minus px, right? Minimize half what? Ax minus b, two norm, right? It's the same thing, right? Okay. Then now let's get a and b. So for illustration, I just random, okay? And it's Gaussian random, okay? And then what? We need the size mn, okay? I just randomly make some size, okay? So a is mn, random, okay? This is a, okay? Okay, plot b, it should be random, yeah, random. And then now I want x, so I will make initial x. Okay, so you can make a function called get inix. So for a lot of algorithm, you will have a start warm up algorithm. For example, for some machine learning, you will run some simple machine learning to get the initial. So you will do this. Here, I just random n by 1, okay? And important, I will always call this ini, initial, okay? It should be random, okay? It's just a random, okay? Then what? If you have initial x, you also have initial f value. So I will have f ini, okay? This example is easy, so I will type the f here. So if I have a and b, then I have q and p. What is this? Okay, so my q will be what? A transpose A. So A transpose A. Okay, what's my P? A transpose B. This is exactly this, right? And then what? I have constant small c. C is just 0.5. What? B transpose B, right? B transpose B. Okay, so PQC. Okay. Okay, make mistake, forgot the star. Okay, so P should be now correct. Okay, good. C should be also correct. Yes, so C is a number. Yes. So my f value will be what? My f value will be just 0.5 times this thing now in matrix is H transpose Q times X. So H transpose times Q times X minus this is P transpose Q, P transpose times X, and then there's a C, so plus C. But for minimization, we actually don't care about constant number because that's shifting the y-axis, but I put it back. So now I have this. This will be my initial f value. Okay. Okay, I didn't have x, I, and I, so this is mistake. So now this is value. So that means if you plot this, this is your y-axis. So now what? We do gradient descent, okay? Gradient descent, okay? Then we have a for loop, okay? For loop for what? K equal 1 to 10, okay? 10 times. We have what? Compute gradient, basically the step. Compute step size, the step. Perform gradient descent, update. And then what? Calculate new f value or f value at new x. That means what? This is get new x by, yeah. So basically it's just this thing. Then what's gradient? Go back to here. Q, this gradient is just qx minus p. Okay, so qx minus p. So gradient grad f is what? Q times x minus p. And here's the thing, I didn't define what is the x, so I will have x equal xi9. So this is my starting point. Then I have this. Let's see. Okay, then now I should have this. Okay, so grab f is a vector. Then what? Step size. So step size, okay. In the notes I use t, here I call it step size. Okay, spell step size. Let's assume you don't know this. Because for some problem, for example, what is this? This is we do exact line search. What's exact line search? You solve this on T. Let's assume this is deep neural net. Then you can't do this, right? Secondly, let's assume this is deep neural net. Then you don't know the L. Okay, this node is what? Quadratic. But you can do it for whatever f, right? So, due to stupid reason, okay, 0.001, okay. Let's do this, okay? And then what? What's the new x? X equal x minus step size time gradient. Yeah. And then what? I just calculate the f value. So f at iteration k, it should be what? I do this again on the new x. So I do this whole thing again. So, but this is not xi9, it's x. This is x. This is x. And that's it. So now, just now run the whole thing. Okay, now you see, I have f, plot f, going down, good. Now, here are plotting. This is very ugly plotting. Okay, first, figure. Then what? You should always make it figure. The reason is this. If you make it like this, okay, so let me run again. You make it like this, usually in paper, if you publish paper, sometimes you have to squeeze this to like this, alright? Then if this is very thin, cannot see. What I will do is, I will make it thicker, line width 2. Now I do this now thicker. Here is the thing, this thing have 10 iteration. 10 iteration, if possible, plot the dots. So I will do this for 10 iteration is, okay, this means color is black, this means put a line, and I put a dot here. Let's say if I do this, okay, then I'll have this is dotted line. In this case, okay, I don't want to do this, but if I do this, let's see what happens. Then I have this is a dot. So, one simple trick will be this. So plus, I plot this, and then hold on, and then I plot black dot, and then now the dot, I want the dot bigger. So marker size, yes, and then make it 20. Now I run this again, yes, this is one way. So this is to plot the line, this plot the dot, and you separate them. And then what? And then you grid on, so now you have what? You have grid. What's next? This one, if you squeeze it like this, the axis label is too small. So you want to do is set GCA font size, not font name, font size, bigger, let's say 16. Okay, let's see what happens. Now this is bigger. Put 160, what happened? Now you see this. Okay, this is just for your knowledge, okay? So just do this. This means get current figure, make the font size big. Yeah, 16. Usually the font size 12, so 12 is enough, okay? And then I do this. Okay, this is okay. But this means what? This actually means if you plot this graph after this and you do not make it big small, this is perfect. But it's possible you will always do this or this, right? Let's say you do this, then this is not good. What's next? Well, you want the label. What's label? Okay, label is X label, Y label. X label, I will call it K or iteration. And then what? Y label is F. So let's say I do this. This is actually wrong, but anyway. Now like this. The problem is why this is not good. Because you want this to be mathematics. Sometimes you want this to be mathematics. So what you should do is, you can type this, but you need to make it interpreter, it's LaTeX. So you make it interpreter and then make it LaTeX. So let's see what happens. Now you see this is now mathematics. But now this is too small. Let's say xk. So now this will show me math. Okay, now this fxk. This is iteration, right? Now I want to do the same thing. So iteration and then I put k. And then what? I just copy here. Okay, and I think these are too small, so I want it bigger. So 16, and then 16. But if I run this after these two lines, it will overlay. It will make it back to 12. So I have to make it back to here. Then what does it mean? It means I will make the grid axis. That means the 1, 2, 3, 4, 5, 12, but the x-axis label is 16. Okay, now let me do it. Now you see, these are bigger than the 1, 2, 3, 4, 5. Okay, maybe you can't see it. Let me go back to, let's say this. Then this will be very clear. Okay. Now see, these are much bigger, okay? But of course, you won't do that, okay? But you may think that this is stupid. No. Sometimes, if you need to have this kind of figure, then this is correct. Okay, of course, 36, too big, okay? 16, okay? So now I have this. Okay, done. Now, let's talk about, go back to algorithm, okay? So, this is what? This is constant step size. This is stupid. Then you may think, oh, this is very slow. Can I make it faster? Of course. Algorithm is about speed, right? So now, let's say I want to compare two methods. Okay, so now I need to make two methods. So what I'm going to do, gradient descent method 1. I call this, and then now I call this F1. And I click Shift Enter, all of them become F1. And now I want to do it again, but using another step size. I want to do what? Change of the setting. So I just copy and paste. And now I call this F2. And now you see, if I do this xi9, I can make sure every time when I run this, I always use the same starting point. That's why I always name something called xi9. Okay? And then what? Now, let's say this is method 1, this is method 2. Okay, so I call this method 2. That's why I have a 2 here. Later on, if you have method 3, method 4, method 5, you may make a new one. Then, let's say you compare 20, then you may ask, wow, I need to do this. No. Then you use cell, but later. Then I call F2. Let's say the difference between F1 and F2 is my step size is 10 times bigger. Now I have this, so now let me run F2. Now I have a bunch of things. Now I want to plot this. Okay, so I just do this again. I just rename this. I put it below, and then F2, right? F2. Here are a habit. I just do this for myself. I want to make sure they are different, so I always do this. So then it's visually better to know, oh, this is for F2. And then again, you cannot use the same color. So I will use blue, let's say. Now let's plot this. Okay, I don't have F1, F2, so I have to redo everything. But actually, I just need to redo this. Okay, now I have F1, F2. And I don't need to worry I'm wrong, because every time when I rerun this, I'm using the same starting point, is correct. Now I go back to here, run. Okay, now you see, I have two curves. So what is F1? Here's the problem. You don't know which is F1, F2. That's why you need legend. You can always click this, but then there will be problem. You see, this thing, you don't want to have data 1, data 2, data 3, data 4. You want name that you define. So you click legend. And now I will going to remove the dots. And then close all. Run this again. Now this. Okay, then you said, oh, I don't know which is which. Well, we remember black is 1, blue is 2. But if you publish this, nobody knows what is what. So you need to add legend. So what I do, I will call it LGD, means legend. Okay, you may say, oh, I just do this. Okay, and then what? Method 1, and then method 2. Yes, you can do that. But I will call it LGD because then I can play with the LGD. So this is legend. So let's see if I just do this, what happened? Now I have this. You see, now it's not data 1, data 2, it's method 1, method 2. Now why I'm going to do this, because I can do LGD.font size. I make it 17. You see, this one have to be after this, otherwise this will become 12. So I have to put this here. So you can think of this is what? This is set grid axis number 12. Okay, this is what? Make legend. This is make them back. Okay, so now I do this. Okay, now this is better. This is very important, because if you squeeze this, and if it is too small, you can't see. And now you know which is which. Good. First thing. Second thing, this is what? This is plot in. So I'm going to make a title. Okay. Method 1 vs method 2. Okay. And then I copy this. This. Okay. But now I'm going to do new stuff. I'm going to make this subplot 1 to 1. So that means I'm going to plot 2. I'm going to plot another one. What I'm going to do, I'm going to plot another one. This one is in log scale. So I will copy everything. And then now I change this to semi-log y. Then y-axis become log scale. And now I don't care these dots anymore. Okay, I just copy this, and then now I will run this again. Now I have this. So now you see this is different. Why? Because this one is linear scale, this one is log scale. If they are very different in the linear scale, this is good enough. If they are very similar to each other, you should use log scale. What's next? You cannot just compare iteration. You also need to compare time. Yeah, always algorithm in terms of iteration is fast, but it's possible. One iteration takes 1 year. Then can you claim it's fast? No, so you need to take time. So I'm going to talk about time. So time, T, okay? Or I will call it T flag. Flag is just flag, okay? T means time, okay? And then what? And then I will do a lot of stuff. So suppose I compute time, so time. Then I will call it T1. K is the top. T flag. Let's say I do this. Now I will repeat this here. And then I will do this here. But this is now T2. Okay? And then what? Now I'm going to make 4 plot. So these are all on iteration. One is linear scale, one is log scale. Now this is what? This is in linear scale and log scale. One is time, one is not time. So this one T1, this one T2. And then what? The x-axis is not iteration. Now it's time. T. Okay? Then I will change here. T1, T2. Okay, now I run this. I have this thing. Basically, T method 1 is rubbish. Okay, this actually is not fair. Why? Because both of them have similar computational cost, but T2 finish here, T1 start here. Look at the time. It's milliseconds different. So actually, this is most likely because of MATLAB, not because of algorithm. So this one is not fair. But anyway, that means what? That means I have to make it more. Okay, iter max. Iter max. So now I make something. Iteration max, right? Parameter. Okay, iter max. Make it 200. Now everything is different. I run everything from scratch. Now I have this. Now you see, if I make it 200, previously I have 10, right? If I have 10, then this I will have something that looks like this, right? Then of course this gap looks very big. Okay, this one, then this gap of course looks very big, but this actually is due to MATLAB. Okay, the reason is you run the black, then MATLAB store in a compiler. Okay, this is computer programming language. When you run the code, actually it has to be converted to machine. So when you run the black, before you run the black, this kind of thing is not converted to machine language, so you need some extra time. But after you run the black, actually you have something translated in the machine. So when you run the method 2, those things are used in method 2. And therefore, that's why it makes method 2 a little bit faster. So this actually is not fair. But this is 10 to the negative 5. We don't care. You care in the long run. Now you can see blue better than the black. And now you also see one thing. This is not accurate. Why? Because for this, there's some period of time, it does not really move. This is more accurate. But then you will ask, what is happening here? There are multiple reasons. First of all, maybe due to MATLAB, sometimes some of them is hard to compute, more expensive to compute, or sometimes this is expensive. It's possible. This is evaluation of function. So it depends on what you compare. Okay, this one, so many factors, close off. Okay, now let's continue. So let me run it again. Method 1, method 1, method 2. This is iteration, linear scale. This is iteration, log scale. This is time, log scale. Is this a complete story? No, I have another 4 more. Yeah, let's make 4 more. So 4 more, right? So 4. Okay, let me make it 2, 4, 4. Okay, so 2, 4, 5, 2, 4, 6. So what I'm going to do, just let's run this. I'm going to produce another 4 more on this, but now they subtract their minimum value. This is now making the code complicated, but this is actually always you need to do this. So now I'll have this, okay? And then now I will have this, right? I will just copy everything. Okay, and then again, these are my practice. I want to make sure I know they are different. I will have this spacing so that I can very quickly tell, okay, they are different things. I will do this. Now I will put a spacing here. Now this is 7, 8. This is 3, 4. What I'm going to do here is everything the same, but now after I do the result, okay, post-processing. And then I call this figure. So I will have something called F min. Min is what? It's the min of all the min you can get, okay? So this is what? Min of all tested method. I'm going to subtract it here, shift the y-axis. So here it's not fx, it's f minus f min. So tax, this is latex, okay, type this, okay? And then I will do the same thing here, and then I will do the same thing here, and same thing here. And then these are minus f min. So now I run everything. Okay, I make a mistake. Yeah, it's big F, okay. Now you see, these 8 figures are the same thing, but they look very different. Sometimes you will say, oh, I have this, it shows me, oh, my error is much better than the black one. Yeah, but if you read in this, actually it's just very tiny. So that means what? In one sense, you can know this trick so that you can try to make your figure look much better than the other and fake other people. Or you know this trick so that you can be a good reviewer. You know that this is fake. So this is 8 figures of the same thing. So what are these? These are iteration, linear scale, log scale. In time, linear scale, log scale. Shift the y-axis by the smallest achievable value. So in this particular figure, this one, the smallest achievable value is not exactly 0. So basically you are shifting it to 0. These have not big effect on the linear scale, but it have very big effect in the log scale. Because you have log 0 is infinity. You can't have infinity. So it will make the gap bigger. So now we have this, then what? So basically every time when you plot stuff, you actually have to plot a figure. And then you see, is it really much better than the black one for all the 8 figures? If the blue is always better than the black, on all the 8 figures, even the most rubbish one, you can be very guaranteed, yes, the blue beats the black. This makes the algorithm absolutely okay. Okay, this part done. Now, go back. We have this. So now I'm going to, what? Not doing the stupid 0.01 thing. Do this too. So L is 2 norm of Q. Then what? Okay, so now I'm not going to do this stupid 0.01 thing. So method 1, I'm going to do the L. Okay, 1 over L. Okay, method 2, I'm going to do the T exact, okay? TEX. Okay, so I need to find what is TEX and L. So, what's L? L is just norm Q. Done. You don't need to type 2 here. It is by default is that. Yeah, done. What's TEX? Complicated. Norm of grad f divided by norm of grad f scaled by Q. Okay, so this one you cannot do it here. You have to do it here. So it will be what? Grad f inner product grad f divided by inner product Q grad f something like this, right? So what I'm going to do, I will compute this. So grad f dot times grad f divided by what? This thing. So it will be Q times grad f. And then what? Dot times grad f. Now run this. Okay. Oh, okay, I see. Okay, now method 1, method 2, stupid name. Nobody use stupid name. So method 1 is GD with step size L. Method 2 GD with exact step size. Okay. So now you see, if I plot in linear scale, you can't see the difference. This is why we plot log scale, and this is also why we have shift. So now this one is a very good example. First of all, ignore this. This is time. Look here, T, that means step size, using exact step size, because exact step size is arc mean of the step size. Of course, it's better than using a L. Okay, so you can see it's always better. Then this is linear scale. We cannot see because in the end, when they converge, but you see still it's always better. So you need a log to make the gap bigger. So now very clear, exact step size is better than L. This is what you shift the y-axis. So in this case, it's the same. This is now better. Why? Because you shift it to 0. Log 0 is negative infinity. So that's why you have this. This actually tells you it's much better.